Hey everybody, Dr. White back. More on infinite sequences. Uh, I'd just like to remind you, an infinite sequence does not necessarily have to converge. How about the limit as n goes to infinity of minus 1 to the n? So if I were to just write out some terms, initial terms of that sequence, I look at the general term and I just let n be 1 and then 2 and then 3. A sequence always starts at 1 unless they tell you otherwise. Well, let me see, I'd get minus 1 to the 1, minus 1 squared, minus 1 cubed, and so on. Minus 1 to the 1 is minus 1. But when I raise minus 1 to even powers, I'm going to get a 1, like here. Here I am at an odd power, minus 1 cubed is minus 1. But the fourth power, even power, gives me a 1. And it looks like I'm just going to cycle around from minus 1 to 1 forever and ever and ever. So there's not one single number that I'm getting closer and closer to 2 as I go further out in the sequence. So the sequence does not have a limit. It does not converge. On the other hand, how about minus 1 to the n divided by n? Does it have a limit? This certainly, the minus 1 to the n causes us to hop around between positive and negative, but there's an n on the bottom, so we're getting smaller positive and negative numbers. What's up? Well, I noticed that minus 1 to the n over n, general term for our sequence, that's always going to be less than 1 over n. And it's always going to be bigger than or equal to minus 1 over n. And when I think about 1 over n, as n goes to infinity, it goes to 0. And as I think about minus 1 over n, well, it's always negative, but as n goes to infinity, it gets to be smaller and smaller negative. It's going to 0 too. So poor old minus 1 to the n over n is boxed in between the two of them, and those two sequences are getting closer and closer to each other. And so minus 1 to the n over n has no choice to go but the same place that both of them are headed. It's got to go to 0 too, by the squeeze theorem. Yep, there's a squeeze theorem for functions, so there's a squeeze theorem for limits of sequences here in Calc 2. The picture to have in your head is the function y equals 1 over x, graphed like this. Here's the function y equals minus 1 over x. And what I've done is I've plotted the points of the sequence. 1, minus 1 to the 1. 2, minus 1 to the 2. 3, 1, minus 1 to the 1 over 1. 2, minus 1 to the 2 over 2. 3, minus 1 to the 3 over 3. 4, minus 1 to the 4 over 4, and so on. So the sequence hops around from being on the top graph to being on the bottom graph, but it's between the two graphs, it is forced to go to 0 like the two graphs do. So the Squeeze theorem is going to be pretty useful. Got another question for you. How about r to the n divided by n factorial? So r here, I'm imagining, is just some fixed real number, like 3 or 2.5 or negative 7, you know. So r to the n, like that, could easily go to infinity really fast. If you start with an r that's like bigger than a 1, r to the n is an exponential with a base bigger than 1. It's going to boom up to infinity really fast, you know. On the other hand, n factorial also gets big really fast. You know, 3 factorial is just 6. 4 factorial is up to 24. 5 factorial is 120. Wow, bigger and faster and faster. How about the ratio? Does that go to a limit? If so, what? So this is another kind of infinity over infinity form where L'Hopital's rule really would not help you because we don't have like derivatives for n factorial. So let's think about it this way. To make our math a little easier, let's just temporarily assume that r is a positive number, and I will deal with the negative case later. Well, if r is positive, then it's gotta be between two non-negative whole numbers, you know? Like there's some number m, where it's an integer, and then the next number up, m plus 1, where r is like in between them. Like maybe r is 867.3, and then it'd be between 867 and 868. Okay, so my m would be the 867. Okay. Now, let's think about r to the n over n factorial. That's actually, you can think of it as little n, different fractions multiplied together. Because there's n r's multiplied together. Here they are. And there's n numbers here multiplied together, and they go from 1 to 2 to 3 all the way up to little n. And what I'm doing is stacking the numbers on the bottom underneath an r on the top. And so I get little n fractions. And I'm looking at the first capital M of them right there. So r over 1 divided by, and then times r over 2 times r over 3, all the way up to r over, that n. Okay? And I noticed that there's no n's in that. So that expression is not changing as n gets bigger. It's a constant as far as n is concerned. I'm just going to call it C for short from here on out. But I'm going to look at the rest of this stuff. That's like n minus capital M fractions there. Okay. And I like to look at r over m plus 1. Like r is here, and m plus 1 is a little bigger. So that's like less than 1. Now I'm going to look at r over m plus 2. Well, that's also got to be less than 1, because the denominator's bigger now than it was with this fraction over here. So this one's less than 1. And if I go through and I think about all of the fractions that are like in between here, all the way up to, but not including the r over n, every one of them is less than 1. And so when I multiply them together, I'm going to get a number that's less than 1. Okay. Now I also have that r over n that I'm just kind of leaving. Well, let's see. I've got my C. I've got something less than 1, and I've got r over n. If I just remove the something that's less than 1, I would get a number that's larger. When I remove the something that is less than 1, I'll have my C and I'll have my r over n. So what I've just demonstrated is that r to the n over n factorial is actually less than C times r over n. Okay, now let's look at C times r over n. What's its limit as n goes to infinity? Well, it's 0, because C times r doesn't change. It stays what it is. N gets bigger and bigger, the limit's 0. So think about r to the n over n factorial. On the one hand, it's less than this thing, which is going to 0. On the other hand, since r is positive, this is also positive. It's bigger than 0. So it's bigger than the number 0 that stays at 0. And so it's squeezed in between the two, and it has to go to 0 as well. Now that was when r was positive. If r was just any real number at all, let's see what we would do. Well, I look at r to the n, and that would definitely have to be less than or equal to the absolute value of r to the n. Would it have to be bigger than or equal to the negative of the absolute value of r to the n? And now I'm going to divide all three of those expressions by n factorial. And I'll think about this one here. Well, that's the problem we had before, where we assumed that our base was a positive number. I know that this has got to go to 0 as n goes to infinity. And this is just minus the same problem we had before. So although it's negative numbers, it's minus something that's going to 0, so that one's going to 0 as well. So poor old r to the n over n factorial is squeezed between the two of them. It's got to go to 0 by the squeeze theorem. So this is a really useful thing to think about. R to the n goes to infinity pretty fast. It's an exponential function. But n factorial goes to infinity even faster, because r to the n over n factorial goes to 0. To be more general about everything we've learned so far, the n factorial goes to infinity faster than an exponential, a to the n. Well, actually, to make an exponential go to infinity, you have to have a base bigger than 1. And the a to the n, we have learned earlier, working with L'Hopital's rule, that it goes to infinity faster than n to a fixed power does. Like we found that the limit of n squared over e to the n was 0, using L'Hopital's rule twice. in general, like if you just had like n to a fixed power k over some exponential a to the n, and like a was a number bigger than 1, the top's going to infinity, the bottom's going to infinity. By L'Hopital's rule, look at the derivative of the top over the derivative of the bottom, and just keep using L'Hopital's rule. If you use L'Hopital's rule k times, you'll end up with a constant here, and you'll end up with a to the n times a bunch of logs of a. That's a log of a right there. And you know, the top will be constant, and the bottom is a to the n is still going to infinity, so the result is 0. So really, it is true that an exponential goes to infinity faster than any fixed power of a variable base n. Okay, that's enough for now. We'll talk about the bounded monotone sequence theorem in our next screencast.